All right. Good afternoon or good morning, teachers and friends. This is Adrian at Computer Science Resources. Today, I wanted to discuss the Lempel Z data compression algorithm. And the reason I stopped at this and the reason I made this slides was because I was working on this APCSP course. And um, on the digital information chapter on the digital information unit, when it came down to compression and compression algorithms, I did not see much in there. There are some algorithms, some basic compression algorithms explained them, but I haven't seen anything like this. I think Lempel Z algorithm will help out students with understanding and appreciating compression better. So I wanted to make this slide, and uh, I wanted to share them with you guys. You can use them during your classrooms as you wish. Okay, so Lempel Ziv is a typical example of lossless data compression algorithm, which basically means that during the compression and decompression process, we don't lose any data, as opposed to lossy compression algorithms, which you can usually find more in multimedia files or other kinds of files where you would uh, be okay with losing some of the data because the quality of the file is not affected a big time. So, but that's not the case with lossless compression algorithm, which is Lempel Z is one of them. The idea with this algorithm is basically in order to compress the data, you will find some repeated patterns in the data, and then you'll replace them with a placeholder or a character or a sequence of characters. And as we will see here, even with binary numbers. Okay. Now, this replacements take much less space than the initial string or image or file or whatever it is. So that's how we achieve compression. Now, let's talk a little bit about Lempel Ziv. It was one of the first compression algorithms ever invented, discovered in the late 70s by Professor Lempel and with his colleague Jacob Ziv from IIT. Other than Hoffman, this is actually one of the most used lossless compression algorithms out there, and it's under the hood in many of the technologies that we're currently using, uh, PDF documents, GIF files, TIFF files, all that kind of stuff. And meanwhile, there were a few other enhanced versions achieving even better compression rates like LZR, LZW, and so on. So the Lempel Ziv algorithm was enhanced since the 70s and the 80s. So how does it work? This algorithm reads a sequence of characters, for example, from a text file, and then it starts grouping the symbols into unique substrings. The objective of this algorithm is to find, like I said, patterns of data that repeat and encode them, save space. So it reads them, it groups them, and then it converts these substrings into binary codes, which we will show how. Because these binary codes take less space than the initial substrings, a compression is achieved. So I would like to, for you guys to take the opportunity to think a little bit about it. For example, let's take the string BBC again, um, VCB, CCBC, BCC, BCCBCC. Okay, it's a string that we are working on compressing it using the Lempel Z algorithm. It has 22 characters at 8 bits a character. Its initial size would be 196 bits, and we will try to compress it. Okay. So here's how this works. Okay, I'm a the first step, I'm going to start reading the characters from left to right. As I go, I'm going to start grouping them, right? I'm going to start grouping these characters into unique substrings. Again, the substrings have to be unique. Okay, that's a keyword here. And give each unique substring an index, okay? So obviously I'm going to start with B. It's on the first position. We have nothing prior to that, so I'm going to give it the index of 1, right? And then I'm going to go the next one. The next character is B. I have B 1 time, so then I'm going to go to the next sequence of characters. I could not pick just B because it was not unique, okay? So I'm going to combine the B with a C, and I'm going to form the unique substring of BC, which I will assign the index of 2, okay? Then I'm going to go ahead and I'm going to ask myself, is B there? Yes, B is there. We have it. We don't want to reuse it because it's not unique. Is BB there as a substring? And it's not. We don't have it. We don't have it yet. So we're going to take it as a separate substring, and we will assign it an index of 3. Then I'm going to go to C. Is C there? C is not there yet. So it's unique. And it does not repeat, so it has a separate index. That's index 4. Then I'm going to go ahead and I'm going to look at the next character. Next character is B, right? Is B unique? No, we have it before. How about BC? BC is not unique either. We have it in position number 2, index number 2. So then I'm going to go ahead and form the very next substring that I can form, which is BCB. And I will assign this particular substring a value of 5. Okay? So I think you guys got the idea. I'm going to continue like this till I finish the string. By the way, these 2 last characters here are CC. They're not going to be unique, but they're the last 2. So we're going to explain how that works. Okay. We're going to explain what we will do in a situation like this. Okay. So now, here's some extra logic when you deal with these types of indexes and when you assign these kinds of indexes, okay? So if a character or substring repeats itself, you do not assign it a new index, but you build a longer substring by adding an extra character to the right. Assign that longer substring an index. A good example would be BCB in our string. And then the only other logic or rule is if the character or substring repeats itself, but it's on its last position, then you can assign it an index, even if it was there before, okay? So that's the only exception to the algorithm where you can repeat some of these substrings is when they are on their last position. So a good example would be CC at the end of the string. We had it in position number 6, index number 6, but we're going to give it the last index of 10. So then you have to make a table like this, okay? And I know this looks a little scary, a little cumbersome, but it's really not. So what we're trying to do here is to go from position 1 to 10, take all the substrings that we have already identified, and do 2 things for each position. First, assign this position's numerical representations. In other words, we want to move away from letters because letters occupy 8 bits each. We want to go with numbers, and eventually we want to go with binary numbers to save a lot of space. And then we encode them. And here's how this works. So I'm going to start at position number 1. The substring is B. I'm going to give it this numerical representation of 0 bit. This is the first character in the string, so it's not much I can do. However, once I made it to the second position here, I'm going to be on BC, right? Good numerical representation for this is I take character B here and replace it with the position of the unique character B that I had it before. So that's number 1 for you. And then I can append capital C here. So a numerical representation of this would be 1C, okay? Position something similar for position number 3, B. I have it as in position 0 followed by a B. So this is going to be 0B for 1. Position number 4, the same numerical representation, 0C. BCB. BCB is an interesting one. I have BC in position number 2. I have BC in position number 2. So then I'm going to replace BC with 2. And then I'm going to put letter B. So that's how I go. I perform the same technique for position 6, 7, 8, 9, and 10. And that's how I end up with this numerical representations of this substrings. Now, the last step is to encode these. And in order to encode them, I can use a convention like this. Remember, I want to save space. So I want to formalize things. And, for example, represent B as a 0 and C as a 1. Okay, that's unique. It's also reversible. I know how to go back from that too, so I don't lose any kind of data. So then I'm going to go ahead and in the numerical representation, every time when I see a B or a C, I replace it with this binary digit here from this table. And every time when I see a number, I will replace it with its own, what do you think? With its own binary code, okay? So 0 binary code is 0B. I'll take it from here as 0. 1 is 1C. I'll take it from here as 1. So I end up with 1, 1. 0B, binary code of 0 is 0. B, I'll take it from here as 0. 0C is 0. C is 1. 2. Number 2, I'm going to have to put down the binary representation of 2, and it's 1, 0, okay? And B is 0, so it'll be 1, 0, 0, okay? I will end up with 1, 0, 0. Four. 4C. 4 is 1, 0, 0, and C is 1. 5 is 1, 0, 1 in binary. C is 1. So as you can see, during the encoding phase, I was able to transform this whole string and make it look like this. Okay? And you can already tell I have many more bits here in this compressed version of the string than in the initial string, okay? Uh, Sorry about that. Let me erase this with a little bit of a eraser here. So I started with this string, with this long string. Well, it's actually not that long, but still at 22 characters, 8 bits each character. I started thinking at 196 bits, okay? And after the compression, I only have 29 bits. So using Lempel Ziv algorithm, we were able to achieve a compression ratio of 14.7, which, by the way, is a fantastic compression ratio. You usually don't see that in real world applications. But for the illustration of this example, it gives your students a very good idea um, of what a compressed ratio will be for this. And the students will also have to be able to appreciate there is a reverse algorithm uh, that this type of compression allows me to also decompress it. If I start with the binary string, I can always go back to the actual string of literals. All right, so this is Lempel Z for you guys. I believe even if they don't become an expert in this type of compression algorithm, understanding this will give your students a better appreciation of what data compression is and what good compression algorithm looks like. And this can be also mirrored and discussed in comparison to other data compression algorithms. For example, run length encoding is presented in CodeHS and in the literature of the College Board. Of course, that's a more trivial algorithm. It's basically find the vowels in a string and replace them with how many times they show up. Uh, a less performant algorithm. So I hope this was useful to you guys. I will also upload the slides and have a great day ahead.